उठा कर जरा अरे साहब को
this pre-submission seminar on title Design and Development of a System for Traffic Density State Estimation using acoustic signals and its application in the intelligent transport system. So prominently this research work is partitioned into two parts. One is the density estimation, traffic density estimation by using cumulative vehicular acoustic signal. And once the density is estimated, we go for the application area. This research work is carried out under the guidance of Sarodisa. Overall, the presentation includes, we'll begin with a quick overview of the introduction to the intelligent transportation system, some of the traditional approaches, what are their limitations, disadvantages, how the modality of acoustic signal is employed, the prominent motivation towards this research work, then there are several objectives about this research work, what literature says, and mainly this work is partitioned into 5 parts. In the first part, we begin with the acoustic feature extraction, followed by the decision of frame size and shift size by using unsupervised learning mechanism, which is self-organizing maps. Second thing is the inherent data which is there in the traffic. So the characterization of traffic, some of the important properties that are concluded in the second part. Third one is the modality of traffic density state estimation using the very well-known neurofuzzy classifier. Then its performance improvement by using the concept of linguistic edges. Then to employ the feature selection mechanism and slightly modify the neurofuzzy classifier of linguistic edges. So we got the better performance there. And how the training time can be improved, training time can be reduced per iteration. That can be carried out by speed up scale conjugate gradient algorithm. So these first 3 parts will cover about the traffic density state estimation. Later on, moving on to the application part of it. So some case studies are there. One is optimal route selection problem, followed by the adaptive traffic signal controller. Then the your speed approach, we have traffic data analysis of Nagpur city, and the traffic congestion level estimation, followed by the concluding remarks and the features. So let us begin with the introduction. Nowadays, intelligent transportation system is the most fundamental system in the world wide today. To this context, a vehicular transportation is, many of the people are rely on vehicular transportation nowadays, and as far as this vehicular transportation is concerned, the density on general on path or freeways is day by day increasing, and there is a reason for it. We have motorization, urbanization, there is excessive population growth. So density of the road segment is considered to be one of the crucial parameters. Now, one thing is, what we require is the effective mechanism. So effective mechanism is now being a major concern of the city authority. So what we require is an intelligent management system which will do the traffic monitoring for us. Okay. Now when we talk about the developing geographies, when we talk about the developed geographies, one of the prominent characteristics of developed geography is the traffic is lane driven, it is homogeneous, it is non-charged. Okay. So this was the primary characteristics of developed region. So to such extent, if we want to do the traffic monitoring, monitoring can be done by cameras, by speed guns, or by loop detectors, or by magnetic sensors. All these approaches are very good in case of developed countries, but these approaches are, first thing is, there are cost associated, so installation cost, maintenance cost, operational cost associated with these devices is very high. Second thing, these devices may not be feasible, or such kind of mechanism may not be applicable in the developing geographies. Now see, when we talk about the developing geographies like Asia or India, traffic is non-lane driven, it is highly heterogeneous, and it is very choppy. So such kind of traditional approaches are not feasible to this context. So what researcher community is doing, researchers community is trying to have some sensing technologies which is based on some, say, laser or radar or sound, ultrasound or audios, or even with the video images. And the primary requirement or primary characteristic that we require is it should be robust, it should be sufficient to handle the environmental conditions, then it should be cost effective, and it does contain a wealth of information. So to this extent, my research work is primarily focused on using acoustic sensors. So the acoustic signal does have wealth of information, that is my primary assumption, and with the help of this acoustic sensor, the traffic density is modeled, whether it is low or whether it is medium or whether it is high. And then there are several applications which are proposed. Now, let us look at some of the sensor technologies which are available. Prominently, it is characterized in two parts, or divided in two parts. One is active sensing, one is the passive sensing. So, all of you can see the radar, loops, magnetic sensing, all these parameters or all these techniques are used for traffic monitoring purpose. But one thing is common in it, they are very costly. Second thing, they are feasible for the small scale. Like if you want to mount it for 1 kilometer road, or let us say 10 or 5 kilometer or small geographic region, it is feasible. But when we talk about the entire city or major concern of the city, then these approaches are not feasible. Now, other thing is we can go ahead with a passive sensor. Like we can have image processing. So video cameras are mounted on the road segment, it will capture the video, sense the frame and get the traffic information. But first thing is it is influenced by the environmental condition. Like if you mount the video cameras, it may not be works in the night condition. That is the first thing. Second, the computational requirement is very huge because once the video is capturing is started, huge amount of data we need to collect. Then this data is sent to server. On server side, the processing is done, and then we will get back the result. So this is also not feasible approach. And second thing is there is a presence of obstacles, and we can say opposition. So two vehicles are side by side, one bigger vehicle and a smaller vehicle behind it. So the detection of two vehicles is not possible. Now to this extent, acoustic signal processing is a cost effective. There are limitations of it. It affects by the surrounding noise. But here I am not targeting on particular human voice recognition. Say hi, hello, word. My target is not recognition of this. My target is if the cumulative roadside acoustic signal is, I want to sense it. So even if this surrounding noise is incorporated. So the limitation of it is now point of advantage for me. So the primary motivation is, first thing, this cumulative acoustic signal is a mixture of engine noise, tire noise, exhaust noise, air turbulence noise and the various noise. So it's a cumulative mixture. Second, the mixture weighting of these spectral components are rely on the traffic density state. Now, whenever we see a free roadway, the noise, overall noise is very less. When we see congested, there are many honks. The engine noise is also there. So at any point of time, so the spectral mixture weighting is rely on the traffic density state. Now to analyze this statement, what we did is we carried out the spectrogram analysis. This one is the spectrogram analysis for the low state, this one is for medium and this one is for heavy. Now when we analyze this spectrogram of low, we see that it has only drive-by noise. There is no presence of honks. Honks are present over here. These are the presence of honks harmonic. These are the presence of honks harmonic. So for a low, it's only drive-by noise. Okay. There is air turbulence noise. Air turbulence noise is generally when the vehicle passes with a high speed. Okay. So typically engine noise or the exhaust noise is very less as compared to this case. Now when we talk about the medium traffic density state, it has mainly drive-by noise. There are some presence of honks and the frequency concentration is in the lower range. Here it is almost equal to 0. It is to the 0.5 and it is 0.02. This is for the heavy. So it is fully present by honk as far as the developing geographies are concerned, and the air turbulence noise or the tire noise are not present over here. So this shows that okay, thus the audio has discriminated information so that we can use it and to classify appropriate. Next. Based on it, several research objectives are formulated. First thing is to estimate the traffic density state. Second thing is to provide approach which is having low cost. Third one is decision of frame size and shift size. This is the important phase of windowing. So what should be the frame size and what should be the shift size. Second thing is to improve the classification performance for the lower combinations of frame size and shift size. Then to improve the classification performance if we consider single feature vector here. To improve or to decide which features are relevant and which are not relevant and their impact on classification performance. Then to develop an appropriate measure which will reduce the consistency ratio of analytical hierarchy processing. This I use for decision making process. Then to provide an optimization based approach to reduce this consistency ratio of ASP. A fuzzy controller are designed for the traffic signal timing optimization for congestion level estimation. The your speed mechanism is provided which will let you know that if you follow this particular speed limit, you will have a minimum waiting time at the next intersection. and a small data analysis is carried out for the small area segment of the contour analysis is carried out. So this entire research work is focused on the vehicular acoustic signal. This vehicular acoustic signal is typically a combination of these four signals. We have engine noise, tower noise, exhaust noise, air turbulence noise and the horn. The engine noise has prominently, when the vehicle is generally stationary or when the vehicle is with low speed, we typically hear the engine noise. Tire noise is due to the two components, one is vibration, one is air. So air noise is generated when the air being pressed in or out of the tire, and the vibration noise is caused as the interaction of tire tread with the road surface. Tire noise we have when the vehicle speed is generally 50 km per hour. Above the 8, then we have a tire noise generally. Then we have exhaust noise. Exhaust noise is generally when the vehicle is loaded. And the air turbulence noise when the vehicle moves at very high speed. Generally we hear a distinct whoosh kind of sound. That's the air turbulence noise. And honks are the manual as to when there is medium to high level of traffic congestion with presence of honks are there. So what literature says. Now basically this and the acoustic modality is employed in the three broad areas. One is the vehicle recognition to identify a vehicle. Second, the vehicle speed estimation. And very few research is done on the density estimation. So vehicle recognition is categorized in two parts, military vehicle recognition and the road vehicle recognition. Speed estimation is one field only, wherein an incoming vehicle, what is its speed. However, this density estimation, there are two approaches again, audio and the other traditional approaches. So in thesis I have incorporated this, but as far as the slide is present, only the literature review of this is incorporated. So let us first talk about what are the non-traditional or non-acoustic approaches or traditional approaches we have. Well, one thing is you can deploy the loop detectors. So given a road segment, loop detector is like this segment. Okay. So whenever the vehicle passes through it, it will sense it. We can also go ahead with the magnetic sensors. But prominent thing is the overall cost with these devices is very high. Second thing is it is only applicable to the known class of vehicle. Like in this approach, it is only applicable to the 6th class of vehicles. So I cannot say people use only 6th class of vehicles. Second thing is these models are also applied on the freeways or on the highways. Still it is costly and the density is fairly well estimated, but it is only two cases. One is it is congested or when it is. People have used also the video cameras. So video cameras are mounted on the street. A particular region of interest is considered. Whatever vehicles are coming to it. See, some of the parameters of traffic are monitored, like traffic count, the average velocity, the lane occupancy. These kind of parameters are generally found, but they have a false estimation due to the small block size of vehicles. And these techniques are only applicable to the developed geographic regions. And I have not seen some of the papers. There are only hardly 2-3 papers wherein the Indian geographic studies are concerned. So one paper is about this. This is a study at the Bombay, IIT Bombay, Riju Rekha Sen. Yeah. So what she did is she used the RF signals, okay, and with the help of RF signals, the traffic density is estimated. This prototype they have just mounted on the outside the IIT Bombay. So density is fairly well estimated, whether it is congested or whether it is not congested. It is reasonably a good study. What they did is every minute they send a data to the server for the analysis. As far as my opinion is to this point is concerned, not every minute data need to be sent to a server. Although it is acoustic data, the size is very few, but it actually is not required. Because what traffic characteristics, it generally preserves for, let us say, 5 to 30 minutes. After 5 to 30 minutes, traffic usually shifts. So even after 15 or 20 minutes, if the data is sent, that will be the reasonable approach. It is a good study. Then we have a data analysis from the consecutive video. So group motion of vectors are analyzed. This is for developed regions. This one is for the binary classification. Is 2 separate algorithms were proposed, one for daytime, one for nighttime. And now, so these were approaches which were for the traditional. Now when we talk about the acoustic, so modality of acoustic, somehow related for the traffic density estimation. The very first research work is by Cotto, where the temporal variation in the acoustic signal is analyzed. So first the wavelet transform is used, so the features were extracted and hidden Markov model is used. But the detection rate was very low here. Here they got a detection rate for known class of vehicle, it is good, but when there is occurrence, when there are few vehicles, there is a lower detection. Okay. And they also mount the video camera just to match that what is my accuracy with video and what is my accuracy with audio. This same again it worked on the acoustic approaches, wherein the system rely on the horns, the vehicular horns. Now, if some particular system rely on the horns, it may not be feasible for the low traffic cases, because in case of low traffic there is hardly a presence of any horn. So that was my concern over here. Next thing is by target. This is the research by IBM, wherein the vehicular traffic density state is estimated. They use SUM classifier and Bayesian classifier. The overlapping class study is, however, not considered in this study. Some of the just the basic paper. Then the combination of horn classifier and MFCC is used, and then followed. This also system rely on the horns, so basically not applicable for the load. So keeping view of all this consideration, what my proper inference says is density can be estimated by using traditional approaches. Second thing is, but these traditional approaches are very costly. So the primary requirement is it should be means what it is applicable to developed regions. So traffic should be lane driven, non-chaotic and homogeneous. That was the primary concern for these case studies. Okay. So this is not possible in the Indian geographic context. So what we require a mechanism which can be applicable for the heterogeneous traffic condition, highly chaotic traffic condition and non-lane driven cases. So we will begin with actual part. So in the first part, a decision of frame size and strip size is carried out with the help of unsupervised mechanism. So now what we have is we have acoustic signals. So traffic data is collected of the Nagpur city, and data is collected on 30 segments. There are around 30 signals are there and 41 segments, because we will show you the area wherein the data is collected. So the acoustic data is collected. Every individual acoustic signal is kept to be of 30 seconds. Okay. The very first phase is the feature extraction. The feature extraction is carried out by the MFCC algorithm. It's a discrete cosine transform of the Mills vector, logarithmic power filter. Okay. So what we have is the input signal. Now while capturing the audio, generally the higher frequencies are lower. Pre-emphasis with boosted higher frequency. Now generally the acoustic signal is non-stationary, and the statistical properties are assumed to be stationary if we consider the short time. So if I consider this is a 30-second audio signal, for a short duration of time the acoustic signal is assumed to be stationary. So windowing technique is applied. Here in this research work, humming window is applied, and to process this entire signal, a effective decision of frame size and shift size need to be taken into consideration. What should be the frame size? So this is my frame size and it is shifted by how much milliseconds. So that is the important decision. My first contribution is on this windowing part of it. So once the windowing is done, so I will have a continuity in between the first and last point of the frame. Then the DFT is used, the fast Fourier transform is used, which will convert time to frequency domain. Then the male filters are applied. There is a special significance of it, because human hearing is non-linear. We are less sensitive to the frequencies which are greater than 1 kHz. So towards 1 kHz it is linearly scaled, but after it is logarithmically scaled. So that's why male filter bands are applied. So 24 male filter bands are applied, and then the output of it are passed to logarithm of it. Logarithmic significance is it preserves the loudness, and when we do logarithm, the dynamic range of values are actually compressed. So that is the key significance of the logarithm. Then finally, the signal is back converted from time to from frequency to a time domain, wherein we got the coefficient. So these are the coefficients. So I have considered 12 coefficients. What literature says, you go ahead with a 10 to 20 first coefficients in a frame. So I have considered 12 MFCC coefficient. One is the energy signal. So total 13 coefficient. Okay. Now one thing is, in many of the cases, derivatives of also it are considered. So delta derivative and double delta derivative. So 13 features are these, 13 delta, 13 double delta. So total 39. But these features vectors are not considered in this study. Prominently it results in, means the classification performance is deteriorated. That's the only reason why these are not incorporated in this research. Firstly, I started with it, but later on I find that okay, the performance is degrades. Now then later on I come to a conclusion why the performance degrades. The key reason is generally there is a change in big feature vectors. So like if I say hi, hello, how are you? So these words are quite different. So change in feature vectors if they are there, these are approved. Here I am talking about a particular traffic density. For a 30 seconds of time, a traffic density is assumed to be stable for one particular class of. That's the only reason these feature vectors are later on excluded. So these phases I have already covered. So this is a question mark now. What should be the frame size and shape size? One way to answer this question. So these frame size and shape size I have considered. So total 6 set is considered. Okay, you go ahead with 40, 20, 150, and last one is 1500 to 50 milliseconds. It is frame size. It should be the shape size. Now typically if it is a ASR system, audio recognition, then 40-20 is reasonably good. But how to rely on or how to decide that which is good? So one best approach is you collect all the acoustic data, do the feature extraction with all these combinations, and then do the experimentation and finally come to a conclusion that okay, this one is good. That's the one way. Second thing is we can have alternate mechanism which will let you know that okay, even if I want to do the experiment, which one is good. So this experiment, one of the well-known techniques is you go ahead with the unsupervised learning mechanism. So here in this research work, for the collected data sets, unsupervised learning mechanism is incorporated, and the very well-known technique is a self-organizing map. So it's unsupervised learning mechanism project. It's map the data in the lower dimensional way. Basically I have the two layers, input layer and output layer, and visualization is also there. So visualization factor will let you know okay, whether we are going in the right direction or not. Basically it has three mechanisms. One is computation, cooperation and synaptic adaptation. What does in computation is, for every input training vector, the neurons in the output layer will compute, and the one which is having highest value of discriminant function will win. So now the winning neuron will decide the topological neighborhood in the cooperation procedure. So these two processes will go hand in hand, and then based on it the synaptic adaptation process is correct. So in sum, there is a short range inhibition, short range excitation and long range inhibition. So those neurons which are there in the closed neighborhood will excite, and those neurons will update their weights, and those which are at the long range will causes inhibition. So there will not be updation inhibition. So actually this topology is physically actually the neurons will try to move in accordance with the winning neuron, and finally the U matrix representation of it will give the visual context of. Now this is the proposed algorithm by using self-organizing map. This is the very first contribution of this research work. So we begin with the input feature vector and the weight vector. Although this self-organizing map is unsupervised learning, just for the visualization purpose I have incorporated category into it. Frame size and shape size combinations are considered. First we will determine the winning neuron. So the one which is having lowest Euclidean distance will win. Now based on it, there is updation in weight. This is input weight, this is learning input minus some x value. Okay. So this is the feature value, and we decide with this value, this factor is decided by the learning rate. So here Hebbian learning is incorporated. Now in synaptic adaptation process there are two parts. One is the ordering phase and another one is the convergence phase. Now what does in ordering phase is, we initially begin with higher learning rate. Okay, so initially the weight adaptation is quite high, but this is actually also called as a forgetting term in case of Hebbian learning. So initially we begin with a higher learning rate, let us say 0.1, but once we go on with the 1000 iteration, there cannot be a same kind of, otherwise it will cause a saturation. So later on this learning rate will reduce. And in the convergence phase, the number of neurons in the neighborhood which are previously excited. So let us say if I take 100 neurons, one is neuron which is winning neuron. So winning neuron cause excitation of initially 50-60 neurons or more may be greater than. This cannot be a case for all the 500 iterations. So even after 500 iteration, it may be case that this winning neuron will cause excitation of self itself or hardly 1 or 2 neurons. So this can be the stopping criteria in this context. Then for every frame size and shift size, we will decide the frequency. What is the distribution in the class level? And the one which, this will be much clear when we look at the result part of it. And the one which is having the less standard deviation will be decided as a frame size and shift size. Let us look at the experiment part of it. So this is the U matrix representation of frame size, shift size, and the corresponding class level. Here categories are just leveled. It has no, the data is unsupervised. So a combination from 40 to 1500 and from 20. So here it is displayed just like, but it starts from 20 and to the 500. Okay. So the our first combination is 40-20. Next one is 50-100, 200-100, 500-200, 1300, 1500 and 500. Okay. So if we consider a frame size of less than 500, so for this categorical region, this is for this categorical region, the categories that are observed are biased towards any one class. We can see the frequency of class 1 is much higher, although the data is symmetrically distributed among the three classes. For the frequencies which are greater than frame size which are greater than 500, also here also the output level is biased toward one. Now only in this region of frame size of 500 to 800 and a shift size of 200 to, we can see there is some sort of equal distribution. So all the three class levels are equally categorized. So that's the key point, that we have concluded that okay, if we go ahead with a frame size of 500 millisecond and a shift size of 200 millisecond, it will certainly result in a best classification performance. So this was the key idea which was initially there. But I cannot certainly rely on this fact that it will give me, so I need experimental validation. So the experimental validation is carried out in the second. So here for all those 6 class of levels, the exhaustive experimentation is carried out, which will prove also that okay, this combination is good, and this experimentation will also lead to the some of the important traffic observations that are not there so far enlisted by me. This one is the experimental setup considered for the Nagpur city. Sampling frequency is 60. I have not purchased even the standard microphone. Yes, mobile microphone is sufficient. Okay. So for one segment around 90 minutes of data is considered. These are the frame sizes. So total number of frames, if we consider this, so a 30-second signal, combination of 40-20. Okay. So if we go on doing this in this 30 seconds, around these many frames are there. Okay. So if we consider time span of 5 seconds, so around 250, 500, 750, 1000, and then 12 and 9. Okay. So this is how. So when you see for smaller combination, there are many frames, and as the combination increases, the number of frames are also increased. Okay. Now, support vector machine is employed in this case. It is one of the very well-known statistical classifier. So it projects the data in a high dimensional space where it is linearly separable, and this is carried out through the kernel tape. Here 5 kernel functions are employed: linear, quadratic, polynomial, RBF and MLP. However, after experimentation it concluded that only linear, RBF, linear, quadratic and MLP results in good performance. Okay, so what we did is, if we consider this entire acoustic signal, take the first frame only. This first frame consisting of 30 MFCC coefficient. So I have a 30 MFCC feature vectors for the very first frame. So this one is the experimentation for a single frame. Okay, and this combination 40, 20, 150, 200 and so on. I have not considered 1000, 1500 and 500 due to because of computational overhead only. Later on I have a slide wherein it will that for one audio signal it takes nearly 1 minute to extract the video. So that's why I excluded that out. So what we come to a conclusion that as this combination increases, the percentage accuracy is increases and later on it decreases. It is very difficult to visualize this, but it is very easy to understand through this. This is the same way graphical representation of it. So I have 40, 20, 100, 200, 500 and 1000. So as frame size, shift size increases, the classification performance increases to the extent of 500 and 200, and then the classification performance decreases. Okay. These are the various kernel functions, so we are getting the best result for the linear kernel function. Again, the funda is same. Frame size, shift size increases, the performance increases, classification accuracy increases, later on it decreases. Okay. So here it again proves that okay, this is a reasonably a good approach, but this is just a single frame. Okay. Now next come to in mind, this was the very first observation, that as this increases, performance increases and later on it decreases. Next thing is, our primary assumption is that traffic density state is assumed to be a stable for some long duration of time. So instead of considering only single frame, why not to consider a contiguous frame? So I have some 1200 frames. So what if I consider the frames which are there for 5 seconds, then the frames which are there for 10 seconds, for 15 and 20, and then analyze it what it results in. Okay. So contiguous frames are considered for 5, 10, 15, 25. And this one is for the first one, for 40, 20, for first 5 seconds, for 10 seconds, 15, 20 and 25. The visual representation is there after these slides. Here also we can see that the classification performance increases when we consider the contiguous frames. Here you can see it is 36 and it is 73. Here it is 100 but it was previously 90. So as frame size shifts, this contiguous frames we consider the classification performance increases. Okay. This increases also, but it has again one limitation of it. I will elaborate later on. This one is for 100, 500. Again, as this increases, the performance increases. This one is for 200, 100, 500, 200 and 1300. This one is the visual representation of all four. So this one is for 40, 20. Okay. The linear kernel function, quadratic and the MLP. This one is a 5-second timeline. This one is a 10-second timeline, and this one is a 25-second timeline. So as number of contiguous frames increases, the classification performance increases, getting the best performance in the context of linear classifier. This one is for 150 combination. This one is for 200, 100. This one is for 500, 200. This one is for 1300. In everywhere we can see the same scenario. As time span increases, the performance is also increases. This one is the overall comparison of all these fours. So 40, 100 and 1000. Here also this color indicates it is 500, 200. So in consideration to all, the one, if we go ahead with a frame size of 500 and a shift size of 200, it will certainly result in a best classification performance. Next, another important characteristic that is observed is, this is the traffic density state. This is low, this one is medium and this one is heavy. We observe that for a medium, the performance is less as compared to low and as compared to heavy. This has prominent reason why performance decreases for the medium traffic density, because it possesses the characteristics of both the cases. Medium traffic will have some characteristics of low and it has some characteristics of heavy. That's why. So there is a problem of class overlap. Later on this issue is resolved in this research work. So it's a class overlapping problem in the case of pattern recognition and classification. So this was one of the observations from the experiment. This one is a elapsed time analysis. As this combination increases, the acoustic feature extraction time required is increases. So for 1500 it is nearly 1 minute. So certainly it is not feasible. Even if I try for this 500, 200, it takes 1.4 seconds. Still high. Okay. But I am getting good performance for 500, 200. So one question is, if there is a minimum time requirement for 40-20, why not to go ahead with 40-20? It results in a lower performance, but the time requirement is very less. So with the help, later on in this research work, the classification performance is improved for the lower combinations of frame size and shift size, and even the training time is reduced for these higher combinations. We will see it later on. One thing that I want to note over here, this one is the result by the neurofuzzy classifier. Previously we have the SVM classifier. So one point is that, irrelevant of the mechanism, you use any of the feature extraction mechanism, use harmonic line association, use wavelet transformation, use STFT, or any of the classifier which is available in the world. The prominent funda is this traffic characteristics will remain same. It is irrelevant of any of the extractor or the classifier. Now this research work is published in this song part, and the traffic characterization part is published in International Journal of Vehicle Noise and Vibration. This is by Induscience. And some literature portion of it and just a preliminary traffic density estimation is published in WCS Conceptions of Signal Processing. Now, coming on to the next part of it, how this modality of neurofuzzy classifier can be incorporated by for the traffic density state estimation. Some of the prominent issues are addressed in this research area now. Here the neurofuzzy classifier is employed, which is wherein the fuzzy parameters of fuzzy system are determined by the neural network. So typically it's a neurofuzzy combination, and it's a multi-layer feed-forward network wherein every node performs a desired function. This is the typical architecture of neurofuzzy classifier. We begin with the input picture vector. We pass on to the linguistic level, having the membership function. Here in this research, Gaussian membership function is employed. I have I have sufficient reason why Gaussian membership. I will tell you later on. So Gaussian membership is employed. It will tell you the degree of membership at this point of time. So for an input feature vector on this membership function, what is the degree of membership? This in all incoming signals are weighted product here, which will give you the firing strength of rule. So at every point of time we have rules. Rules are set in fuzzy systems. So the firing strength of a particular rules is determined in the fuzzification layer. Okay. Now this firing strength is passed on to the defuzzification, wherein its sum of all firing strength is determined. Sometimes this sum exceeds 1, so a normalization is required. So here is the normalization, and at the output will decide to which class level the given input vector is belong. That is what in general a standard neurofuzzy classifier is designed. This is the same description I have covered. Now we have modeled this NFC on our data sets. So 4800 and till this, we can see that this performance is slightly good. Previously, when we have employed SVM for 40-20 combination, none of the there are only few results which is in the range of 90s. Here, for only single frame, we are getting the best or good performance in somewhere even 95.5. All are in the range of 80s. So slightly good for a single feature. So even 40-20 is reasonably good now. Now again, this performance is improved with the help of linguistic agent. So linguistic agent is first proposed by Latif Sahar, which will convert the meaning of this linguistic level. So if, let us say A is the small linguistic term, the meaning of it can be converted by with the help of this power. So to the membership degree, if I certainly apply the power, its meaning can be changed. So previously it was small, then it was very small. If I go ahead with a power of 2, so I have concentration and dilation. This mechanism can be incorporated to improve the classification performance. How? So I have used Gaussian membership function. This one is the bold and blue is the normal for 1. This one is the concentration part, and this one is the dilation part. We could have used the triangular membership function, but here it is restricted to this point. And Gaussian membership function, we have flexibility. That's the only reason why Gaussian membership is incorporated in this research. Second thing, in Gaussian membership function, the parameters are very less. There are only 2 parameters. One is the center, and the second one is the width of this Gaussian function. These are the only, which can be sufficiently obtained by using any of the conjugate gradient mechanisms. So now how this H values are affect on the classification performance. So let us consider 2 fuzzy sets A and B and 2 feature vector M1 and M2. Okay. Let us keep this as a constant. So power value of this is 1. Okay. And now here I am manually tuning some of the power values. Let us say, just for example, here I have kept the power value of 2. Here it is 0.5 and here it is 0. 0 means I am omitting this feature directly. So if we do the mapping on the corresponding classification performance, this is the degree of belongingness to that class. Here it is degree of belongingness. Here it is the degree of. So what it tells us that if we do a certain sort of a training on these H values, it will result in a better classification performance. That's the key idea. Okay. So a one layer is added in the previous architecture. That is called as power layer. That's it. So whatever input we got from the first layer, a power layer is added to it. And now I have 3 parameters need to be tuned. Okay. So one is what should be the center. See, these membership functions are not fixed. These are changed with the tuning is done with the help of scale conjugate gradient mechanism. So now I have 3 parameters. One is center, one is the width, and next one is the power. Power I can take any value in between 0 to 1. 0 to 4. 4 for the concentration level, 0 on the dilation level, 1 is the neutral. Okay. So for a 0 to 4, I have this power values. Okay. So it results in also a good performance, classification performance. When we compare the neurofuzzy with linguistic edges, then in feature selection, then it will be slightly clear. So as compared to neurofuzzy classifier, this test recognition is good as far as these traffic density states are concerned. Now, one of the conclusion of our previous portion is that this traffic accuracy for the medium traffic is always less as compared to low and heavy. This is due to the fact that it possesses characteristics of both low and heavy. Alternately, it's a class overlapping problem in the theory of pattern recognition and classification. This can be attempted by using the feature selection mechanism. So, if I have 13, 20 features, let us say some features are really relevant, they may not be applicable. So, how to identify which are the relevant features? So, feature selection is incorporated. Same linguistic hedges concept is used in this research work for the feature selection mechanism. Let us take a simple example. Let us say I have two rules. Let us say these are the two input, these are two fuzzy set, and this one is the power value. Okay. So let us say if x1 belongs to fuzzy set A1 with a power value of 1 and x2 belongs to fuzzy set A2 with a power value of 0. Then the output is, let us say, class C1. And this similarly is the second. So here this power value of this second feature vector is what? 0. So I can omit this feature vector actually. So now my rule is reduced to x1 belongs to A1 with a P1 and then it belongs to. So initially I have two feature vector x1 and x2. Now I have only one feature vector. Means it indicates that the x1 is only relevant to this context. x2 may not be applicable. So this is how linguistic hedges are incorporated to improve the or to do the feature selection, and later on with the selected feature the classification performance is improved. This one is the overall algorithm for the feature selection. Initially we thought of it go ahead with a 0.5. Initially kept it all values kept it to 0.5. Later on we'll do it training. So after tuning a sufficient set of classes we got, set of feature vectors that we got, and generally I have considered in this research work if there are 13 substrat coefficients greater than 50%. So first top 7 feature vectors are employed in this research. So what we obtained is, see, these are all data sets. These are the feature vectors. It is arranged in the order of their decreasing power values. This feature vector is having higher power value 3. So it is actually a summation of all the 3 class levels. So I have low, medium and heavy. What is the contribution for low, for medium and for heavy? So feature 1 has 1, 1, 1. So the summation is 3. So the power value of feature 1 is 3. So these feature vectors are considered. So these are the selected feature. This shows these are the selected feature vector for these data set. This one is the selection graph. So 1, 3, 6, 7, 9, 11 and 30 are the selected features which are listed over there for 500, 200. These are the selected features out of 30. Now we can do experimentation with only selected feature. It will again improve the classification performance. So classification is carried out with the selected features, and so this were initially all 13. This is the rule base of all 13 feature vector. Now after selection I have only 7. This one is the performance comparison. So feature selection with linguistic hedges. Now these are the results, and when we compare it, all the 3. This was the standard neurofuzzy classifier. This one is improved classifier with the help of linguistic hedges. This is again improved version with the help of feature selection. So we can see the classification performances were increased. So here it is also stable, but here we got 95 and 91% of classification performance. So the slightly all this thing is done for the single feature vector frame, not for even if I consider contiguous here, certainly the classification performance in all the cases above 97 to 98%. So if I compare with the existing approaches, is it audible? If I compare with the existing approaches, we find that we are getting the best classification performance as compared to the previous. Now, one thing is when we analyze this time span, elapsed time analysis for all those feature vector frames, one thing is, one prominent research for lower combinations, you got the lower classification performance. When we consider contiguous frames, the classification performance improves. But consideration of contiguous frames means you are actually enlarging your data. So now we have very large scale data, and when there is a large scale data, certainly it will take some time per iteration. So how to minimize it? So that's the primary concern. And here in this research work, a speeded scale conjugate gradient mechanism is employed. This one is proposed by author in 28. So what we have is the initial data set right now for 200, 500. So I have considered only the higher combinations. Okay, because for them the time required is high. And then after feature selection mechanism, so these are the selected features. So this data set is now reduced to this extent, and it is observed that around 55 to 75% of training time is reduced per iteration. That's the key significant. So this can be the reasonably good approach. Now this fuzzy portion is published in International Journal of Fuzzy System, is SCI Index Journal by Springer, and the this speeded scale conjugate mechanism, also time optimization, is published in elsewhere procedure of physics. Now moving on to the application part of it. So with the very first application, so traffic density is so far estimated. Now what about the application area of it? So if we estimate the traffic density by using acoustic signal, what can be the application by of it? One is optimal route selection problem. So the fundamental here slightly means there are initially I thought of it 3 class levels. Later on I have considered some 7 class levels. So very low, low, medium, high, and very high. Okay. And there are many actually attributes that can be considered for the comparison. But more or less many of them are contributing to traffic density, like encroachment, parking on the road, the road width, passenger car unit, are more or less contributing to the traffic density scale. So what we thought of it, this is previous work what we did, what is done so far. So here multi-attribute decision making is employed. So it is subfield of multi-criteria decision making. So Broadway is multi-criteria. If your criteria is objective function, it is a field of optimization. And if your criteria is about the attributes, then it is a multi-attribute decision making. So this is the area segment. Let us see the source and this one is destination. I have 7 routes to go from this one source to a destination. Now the question is which one is good or which one is optimal. Even if we Google it, it will give you the route which is on the shortest path. Just now they launched a theme of based on the current density parameters. So let us take a density for 7 routes in 6, 7 am, 10, 11, 2, 3, 4, 6 and 9, 10. Let us, for a case study, let us take an example of 4, 6 pm. So very high, above medium, high, very low. These are the traffic density. This is the fixed distance. This one is the minimum travel time which is required for that path segment. And these are the number of signals, number of intersections from source to destination. That is the count. Now here all these 3 parameters are quite fixed. The only dynamic thing is what? The traffic density, which we have estimated by using algorithm. Now the question is which one is the optimal route? We can see if we Google it, it will give you route 2 and route 5 because it is 4.6 kilometers, the most shortest path. So it will give you that. But experiment result will tell you something different. So the very first mechanism that these are traditional mechanisms that are incorporated. Very first one is simple additiving, which is SAW method. Once the problem is formulated, the normalized decision matrix is computed by identifying beneficiary and non-beneficiary attributes. Beneficiary means higher values expected, like efficiency of machine. Non-beneficiary means lower values desired. Say for example cost. Okay. So by appropriately dividing the normalized values, so we have a data which belongs to different domain of unit. It's converted into a normalized format. Once it is normalized, for every attribute, its corresponding weights are decided. Now this is a user preference based. Here we are not solving a problem for social community. It's a user preference based, and the normalized matrix are multiplied with the weights, and here we got this score, and the alternative which is having highest score will be ranked as 1. Let us take an example. This is routes 1 to 7. The previous data is now normalized. So 4.2 is the shortest path. So it is 1. Now if it is 1, other value should be less than 1. So this value divided by this. So it is how it is normalized. These are the weights that are obtained by using a simple point method. Simply take you can use this scale of 10, 20, 30, 40. The one which is not so important, give a value 10, next 20, next 30. Make a sum of it, divide every value by that sum which will give. Here I am quite comfortable with this approach, model as per my convenience. So here I got the weights. Now this value is multiplied with this plus this into this. So there I got this score. So here route 4 is a certainly good approach. So although route 2 and route 5 is the shortest one, route 4 is the option. So because it is having the highest score. let us talk about weighted product method. This method is quite similar to the previous method. The only difference is in the last. The weight normalized values are powered to the weight and followed by the multiplication. So this is the same normalized value. This to the power of this into this to the, that's why the name given is weighted product method. The weights are kept fixed by using this simple point method. Here also the result obtained that okay, this is good. The root 4 is good. Now one question that can arise is whether these weights are correct or not, because we have decided this parameter. So the question is how relevant are these weights? Now just to answer this question, we have AHP mechanism, which is analytical hierarchy processing. Now this mechanism comes up with a validation procedure, which will, once the weights are obtained, the question is whether these weights are correct or not. So we have systematic validation procedure. It will tell you that whether the weights are correct or not. So here we prepare a comparison matrix. So this is the comparison matrix. Here attributes are compared with attributes. If an attribute is compared with itself, the value is 1. So diagonal will be always 1. The lower portion is just a reciprocal of upper portion. Now these factors come by the Sati scale. So Sati has invented this mechanism, but one indicates that distance is equally important to density. This is my opinion on this context. Distance is strongly important as compared to travel time. 1/3 indicates number of intersections are moderately important than the travel time. So as far as the Sati scale is concerned, this matrix is prepared and the geometric mean of this matrix results in the weight. So this is the geometric matrix calculation and these are the weights. Okay. So now the again question is whether these weights are correct or not. So then we have a systematic validation procedure and finally the consistency ratio is calculated. This consistency ratio should be less than 0.1. That's the key idea. Here I got 0.04, which indicates 4.3% of error. That is allowed. Sati says 10% of error is allowed. So here I got 4 points. So certainly these weights are good. So once we got the weights, simply apply the saw mechanism to get the result. So again root 4 is selected as 1. Then we have a Topsis mechanism. It's a technique of order preference, similarity to ideal solution. So normalization is carried out by a slightly different mechanism over here. Then the normalized values are multiplied with the weights. Weights are again calculated by using AHP mechanism. Then the best alternative and the worst alternative is decided. So that is V plus is best, P minus is the. Now the separation of every alternative from this best and worst is calculated, which is called as a separation measure, and the relative closeness is decided. How it is relatively close to the ideal solution. The one which is so far relatively close to the ideal solution will be ranked as a 1. So for distance, density, this is good, this one is worst. These are the separation measure of all 7 alternatives from good and from bad, and these are the relative closeness of all 7 alternatives. The one which is highly close to ideal solution, let us say ideal solution is 1, 0 is the worst. So 0.86 is the height, that is ranked as a 1. So root 4 is ranked. Prometheus method is also applied, same as the previous, slightly different in context of comparison. So for every attribute, the alternatives are compared here in this case. So it results in a binary matrix. The weighted product of this binary matrix with weight results in a weighted matrix, and based on that weighted matrix, the incoming flow, leaving flow and net flow is decided. The one which is having highest net flow should be ranked as a 1. This is the experimentation for all 6, 7 am, 10, 11 am by using which mechanism SAW, WP and AHP Topsis. Prometheus is also there, just for due to these limitations I have not incorporated in next slides. This one is for 10, 11 am. This one is for 2, 3 pm, which root is ranked 1, 9, 10 am. More or less these methods will give you similar kind of result. Okay. This one is by Prometheus. Okay. So what we got is this. The main key point is not how to apply these methods. The key point is at this point. Here, if we apply any of the traditional method, for 10, 11 am, the root selected is this, but this is wrong. This happens because of that 4.3% of error. Now the question is how we got the answer by all five mechanisms, that you go for 10, 11 am, you choose the root number 7. This is root number. This is 2. This one is 4, this one is 7. For 10, 11 am it says For all it is okay, but for 10, 11, and it says you go ahead with the root 7, all 5 techniques. This only happens due to because of this 4.3% of it. So next question is how to improve the consistency ratio. So I have proposed a optimization based mechanism to improve the consistency ratio. So inconsistency in this pairwise comparison matrix is one of the key research work in case of this AHP. So the consistency ratio is the division of consistency index by a random index, and typically this value should be less than 0.2. In my opinion, its value should be 0. So for 0% error, the decision making is perfect. So people have used genetic algorithm, particle sum optimization and colony optimization to tune this consistency ratio. But when I have gone through this research paper, if I have I will go back again. Let us say if my decision is like this. If I apply genetic algorithm, later on in the experimentation, this 5 is replaced by 9 or 5 is replaced by 0. How can this 5 will be replaced by 9? So means something which is equally important first, and later on after tuning it goes to extremely important. So all the previous approaches, they just have tuned the matrices so that the consistency ratio should be equal to 0. My funda is slightly different. These mechanisms, they come to a conclusion that consistency ratio is now minimized, but the statistical or experimental results are not so good. And the next question, there are many of the optimization algorithms that we can go ahead with, but inherently all these optimization algorithms have some of the limitations. So proper tuning of parameters is required, like in genetic algorithm crossover rate mutation. So my research is not focused on this optimization. So I need a technique which is algorithmic parameterless. So TLB is one of the techniques. So it is invented by Rao of SVNIT Surat. It has two phases, teacher phase and learner phase. In the teacher phase, the one student which is having highest knowledge is considered as a teacher, and the mean of population is calculated, and the difference in the teacher and this mean is added to the every learner. So this is how in teacher phase the overall objective function value is improved, and later on in the learner phase, student will do interaction with one another. The one which is having good knowledge will share its knowledge with the another. So now what my proposed mechanism says, we formulate the decision matrix, we will do this pairwise comparison matrix. Now the next thing is the identification of, so every optimization algorithm will input as a variables. So the next thing is which are the substantial variables. So our selection is from only upper triangle. So consider first row for the distance. I have 1, 5, 3. Only distinct values are selected as a variable. So 1, 5, 3. In next I have 5, 5. The only distinct value is 5. Here I have only one option, so 1, 5. So these three variables are selected. So x1, x2, x3, x4 and x5. Okay. Now why distinct values? Because if my preference is 5 and 5, so after tuning also what will be the result? It will also be same. Let us say it is 5.2, so 5.2 and 5.2. So the expert or user preference should be preserved. That's the key idea over here. So with this identification, this is a small pseudocode of this algorithm. Now once the values are decided, I will limit these values. I have option tune it from 1 to 9. 1 for equal importance, 9 for extremely important, as per as the Sati scale. But I will not allow it to tune for all those 9 values. What I will do is, although this decision matrix is prepared by the expert, I am assuming here that even expert will make a 10% of error. So if the expert opinion is 5, means he is slightly confusing between 4 and 6. So for that variable x2, the lower range is 4 and the upper range is 6. So after tuning, whatsoever will be the value, it is only in the range of 4 to 6. So 10% of error is now handled. So this is the lower bound and upper bound for those variables. Now this is the overall teaching learning based mechanism algorithm, and this one is how the consistency ratio is calculated in the analytics. So this consistency ratio is passed on as an objective function to this optimization algorithm, wherein all those variables and their upper and lower bounds are placed, and finally we get the minimized consistency ratio. So this is the tune matrix. Initially this was 5, 5, now it is 5.0 to 5.02. This is 1 by 3 and now it is 0.49. So 1 by 3 is 0.33. So this is increased to 0.4. Now, the consistency, if we evaluate the consistency ratio of this matrices, it is 0.01. So, from 4.3% it reduced to 1.8. Okay. So, that is a good significance, and if we correlate with the result by AHP for 10 11 am, by if we use original AHP, 4.2 is the good answer, but it is actually, this is the second preference. Seventh one we got previously, but actual answer should be 4th. So in previous diagram 10 11 we have deleted are displayed on this side. Root 7 was displayed by previous mechanism, but due to because of that 4.3% error, our decision was wrong. So root 4 is good. So this was the conclusion. This multi-attribute decision making part is published in KS2 transactions on Internet and Information System. It's SCI index journal, and this teaching learning based mechanism is accepted for publication in Evolving System. This is by Springer. The revised version of it is submitted. It is now in review. Now coming on to the last part of this research, we have adaptive traffic signal control, US-split mechanism, and the traffic data analysis. Let us talk about the traffic signal control. This is review on this context. So the proposed work is mainly divided in two phases, this traffic signal control. One is the phase selection. So if we consider any signal as intersection, I have 4 phases. So out of these 4 phases, which one to select? And after selection of phase, what should be the green time for it? That's the key. This one is a proposed architecture. So at a particular signal as intersection, the queue length of all the road phases will be input. It will pass on to the membership layer for the fuzzification. Through the fuzzy inference system, rule base are provided. After defuzzification, we got the output. Okay, which one is the selected phase? Now for this selected phase, what is the queue length of this selected phase? What is the arrival rate on that selected phase? It will be much clearer with simple example. So this will pass on to the next architecture, and as a result, we got the green times. For example, if we consider this geometry, let us say A is going to end now. So after A, the only option is B can go, C can go, or D can go. The one which is having highest queue length will get a chance. So for example, if C is having the highest queue length, let us say queue length of some 50 meters. So this side will get a chance. So this signal will be green. So C will get a chance. So these are the phases direction. This one is a membership function for the queue length. So low, medium, long and heavy. This is on the queue length. And now once the queue length is decided, what should be the green time or green time extension of it? So queue length along with the vehicle. So if some lane is now green, what is the incoming to that lane? So that is the vehicle arrival rate. So let us say the vehicle arrival rate is this. So based on this, what should be my green time? Whether I should decrease it, make it constant, or I should increase it. Okay. So the experiment result says that around 30% of time is reduced. 30 to 50% of time, waiting time at the signal is reduced by this mechanism for variety of incoming vehicles. This is the US-split approach. This one is mathematical based, right? This will let the user know at one particular intersection that what should be the speed range you should follow, so that you will reach to the next intersection and you will have a minimum waiting time at the next intersection. So this one is a mathematical formulation. So density is also incorporated. Speed limits are also incorporated so that user will comfortably manage it. This is also a simulation experiment shows reach up to 0.6. I don't have data for 0.7 and 8. So it's sufficiently reduction in waiting time. Then the contour analysis. This one is the contour analysis for the distance. So this is the source 1. In 1 kilometer range where you can reach. In 2 kilometer where you can reach. 3 can. This is the distance map. This one is the time map of this considered area segment. If this is the source, in 60 seconds you can reach to this. In 120, in like 7-8. These are the portions wherein you can reach. Finally, the traffic congestion level estimation. This is divided in 2 phases. One is congestion index estimation. Next one is congestion level estimation. Congestion index is estimated by using 2 parameters. One is travel speed rate. Second one is very low speed rate. Travel speed rate is the amount of very low speed rate is upon how time you are spent in delay. and the travel speed rate is your vehicle speed is now reduced due to because of congestion, that is travel speed. So based on these two input parameters, the congestion index is estimated. So this is travel speed rate, this is very low speed rate, and this one is the membership for congestion index. These are the fuzzy rules. If very low speed rate is low and this speed, then the output should be low. This is the experimentation. So this is to and fro direction. Let us say this travel speed rate is this, very low speed rate is this, the congestion index will be this, and if we incorporate density, the congestion level will be this. So during maximum peak hours in the Nagpur geography, congestion level may reach to max 0.6 or 0.2, not more than that. So the conclusion part of this thesis, this research work,
Within 1 hour.
this is the good combination, and the classification accuracy increases as time period increases. Classification accuracy increases for the primary window size and shift size increases. Average classification for median is always low. Linear kernel is best suitable in this context. The time analysis for higher combinations, it is much higher. Traffic characteristics is tells them which is irrelevant of any of the classifier or abstraction. These things are modeled to improve classification performance, and this performance is further improved by linguistic edges and feature selection. Now, this is all I have discussed. 60-70% of training time is reduced by using SSCG. Now, optimal route selection problem is attempted by using MADM. Consistency ratio is reduced by TLBO. The various algorithms are proposed and evaluated. Traffic signal controller, US speed approach, traffic congestion level estimation, congestion index estimation, all these things are. Future scope is certainly we can think of a sensing technique which can virtually work for all weather conditions. And second thing is when we go ahead with large sensory networks, so since traffic signal optimization is non-linear in nature, swarm intelligence based mechanisms can be used. So traffic signal timing optimization by using a optimization method like ACO, PSO, this can be employed. Currently I am working on it, so which result in minimum waiting time at the intersection, and several signals need to be considered parallel, not just for a alone intersection, but for entire geometry. A clear definition is required. These are some of the references I refer in this context. This is my concluding part.
Your voice and your slides are much clearer. I had much less difficulty in understanding what you mean. So where exactly again you pin down your contribution to the most critical
significant part is the decision of frame size and shift size.
Okay.
Next thing is the traffic characterization, which I have noted. Like medium will have low performance. Then as the frame size shift size increases, the classification performance increases. We can improve the classification performance when we consider the contiguous frames. So these were not noted somewhere. So through experimentation it came to know. Next thing is if I for lower combination the performance is decreases, but for the lower combination the computational time requirement is very low. So on one hand I am getting good thing, but on the other hand the computational requirement increases. So the neurofuzzy classifier, the selection of linguistic edges, the modification in this context, and to improve the classification performance for the lower combinations of frames. So this is the key point wherein I have. Second thing is to reduce this consistency ratio of ASP in an effective manner.
So overall, do you think your model can be used in dynamic situations?
Sure. Yes.
Where I would like to say that what you said, you want to plan a route for a vehicle.
Yes.
Given the current status.
Yes.
So what will be the computational requirement, because you have to monitor so many different traffic intersection
Let
points?
us say if a small hardware prototype of the acoustic sensing device is mounted on the road segment, every after 30 minutes, or let us say we keep 30 minutes, every after 30 minutes it will capture a data of, let us say 30 seconds. It will send it to the remote server. On remote server it will be classified. whether it is low or medium. And certainly then other statistical parameters are fixed. Like if user selects source to destination, the distance is fixed. The number of signals are obtained. The only dynamic value is the density. Fairly we can use even we apply the SAW method. That is enough. No need to go for the optimization method. Even we can apply SAW or ASP or some of ASP is suitable. So into this context, then dynamically user can come to know that okay, this route will be good.
So how many multiple processing you have to do in a city? Let's say Nagpur maps. If you want to go from one, say 5 kilometers, 10 kilometers away, how many intersections typically you will have to cross? Typically, just
for 5 kilometers.
Back of the envelope, 10.
Four or five. Yes.
So you'll have to process all these 4-5 data together, right? In order to figure
Yes,
out
all
what's
four
happening.
segments of data,
Right.
and then cumulative traffic density. One thing
Cumulative
is,
traffic density.
one thing is we can so let us say there are five signals. So one segment, second, third, fourth, up to this 5. For this segment, maybe density is low. This is very low. This is medium. So let us say cumulative density of that source to destination. That can be incorporated.
And what are the timing for? So what is the frame speed that you suggested? The optimal one?
500 millisecond and 200 millisecond. Frame size of 500 and shift size of 200 millisecond. In traffic density estimation context, not for generalized ASR systems.
And the result you showed for single frame was how much? The best?
95.56.
For with a single frame.
Yes. And SVM for contiguous frame it is 97.78.
That's pretty good. You were saying these are cost effective. I can see that acoustics.
Yes,
So what sort of errors in real life scenarios?
Yes, if we consider some of the adverse environmental
So
situations.
think again of Indian situations.
Yes, yes. If we consider heterogeneous traffic, so it is okay. But suddenly Shadi band came, so this model will not be here. So
Positions and all that.
in such cases we can separately tune the model with a different class. Okay, if such kind of voice can come, we will
Keep
just
it away
load
from
it
all
to the
that.
previous.
Yes, okay.
Maybe in rainy season it will not be applicable.
Rainy season,
Rain.
no problem.
That's the problem. But otherwise it is reasonably good.
So thought I'll ask, I'm forgetting. Let me think again. So you have justified the numbers that you have used, that is better. Which is good. I didn't understand much about that last part, the route selection. Why do you call it? You said something about the optimal route selection. So the absolute last part of your book. So what are you doing there? Just very quickly push me on.
Optimal route selection.
Yeah, this part.
About this thing.
This part. Yeah. Correct.
See, whatever routes that we got by using traditional approaches, SAW, WPM, AHP, TOPSIS and PROMIC, the routes are obtained and the prominent component for this result is the weight vector. What is the individual contribution of every attribute? So that is obtained by weight. Here we have obtained by weight by using the AHP mechanism, analytical hierarchy process. Whatever weights that we got are with a 4.3% of weight. Now the question is whether this 4.3, Sati says that less than 10% is allowed in your decision making. Here I got 4.3%. Now the next question is whether this 4.3% is really matters or not. Okay. So if I want to reduce this consistency ratio, because 0 is the best thing. So how to reduce this consistency ratio? The only available technique is go ahead with the optimization. Either do traditional optimization or use any of the advanced optimization. Comparatively, I can use ACO particle swarm optimization here, carry out the reduce the consistency ratio, so that whatever weights that I got are actually correct. So ultimately, my decision making will also be more accurate. That's the key idea.
So what did you actually do? You had the matrix, right?
Yes. Here, first thing is the actual problem is formulated. Distance, density, travel time, signals for 7. That's the step number 1, the formulation of the problem. Second thing is we do the normalization. So beneficiary attribute, non-beneficiary attribute. There are other mechanisms. Use Euclidean distance, use entropy measures. In way, normalize the data in the form of 0 to 1. So here we have a normalized data. Now the next thing is what are the weights. Weights are calculated by using this matrix. So this is pairwise comparison matrix, which is this. So now I have prepared the pairwise comparison.
So this one, why is it 1, 5, 3, 5, 1 by 3?
Yes,
it
is based on the Sati scale. Sati scale of relative importance. The scale is 1 to 9. 1 stands for equal important, 3 for moderate, 5 for strong, 7 for very strong, 9 for exceptionally strong. And if you have doubt somewhere, use 2, 4, 6, 8. Okay. So if an attribute is compared with the attribute itself, always value will be 1. So diagonal will be 1. Sati suggested the lower portion of this triangle should be just a reciprocal of upper, because we are comparing attribute by attribute. Now the only key feature is how to prepare this upper portion. So I am comparing distance with the density. For my opinion, or from my point of view, distance and density are equally important for me. So distance is equally important as compared to density. That's why 1. Distance.
What are the other parameters? PT is travel time.
Travel time, number of intersections. So distance is very strongly important as compared to the minimum travel time. This one is minimum travel time. And distance is moderately important than the number of intersections. So this was the consideration.
You are just ranking these 3 parameters with respect to the
if this is good than this, use 1 to 9. But if this is good than this, use 1 by. That's the idea. So this matrix itself, the geometric mean of this matrix gives the weight. And if the consistency ratio of this matrix is equal to 0, means whatever weights that we got are correct, means our decision is correct.
That X comes out how?
See, I have to apply any of the optimization algorithm. Even if you apply any of the optimization algorithm, the variables is required. Okay, so I have to tune this these 3 parameters. This upper triangle I have to tune. So let us categorize into the variables. So for a distance, I can only have option of 1, 5, 3. So distinct values is 1, 5, and 3. Now say here expert
variable.
Here expert opinion is 5, 5. So I will keep only 5, not 5, 5 2 times. Otherwise this will be some 5.2 and this will be 5.7. So user expert preference will be lost in that case. So that's why only distinct values are kept.
Okay, good. I think I don't have any more questions.
Thank you, sir. Thank you, audience.
With this, we come to the end of this PhD pre-submission seminars of 3 research scholars of computer science and engineering. On behalf of the institute, I am extremely thankful to Professor Supratim Biswas for accepting our invitation and for being here despite of his busy schedule. And he had already been there for conduct of the pre-submission seminars earlier as well. And we seek more guidance in future as well. Thank you one and all for patiently hearing.